Purpose of this is we want to kind of dive back through some more of the advanced side of the refrigeration cycle using the various readings, the four basic ones, how the different conditions are going to affect those readings, what they're doing, and just make sure we fill in any gaps. This will be a good refresher going into the summer. Four most critical readings, I think your two saturations, your evap saturation, condenser saturation. Subcool, superheat are the other two. The four are equally important in their own ways. A lot of people would probably make a case that superheat and subcool are the most important. I would challenge that because without saturations, you have no superheat or subcool to begin with. A big part of what we've got to look at is those saturations give us a really defined line of just what the general condition is in that system. What are the basic parameters we're shooting for the most when we start talking saturation? Like let's start off with the evaporator. What are we looking for?
40 degrees.
40 degrees. What's a acceptable range that you would typically shoot? 35, 45? From a broad perspective, yes. Evap sat, our goal is 35 to 45. Now, if I was to really do a deep dive on that, I would critique that even further and talking about, honestly, by the time you start touching that 35, you've already got a problem somewhere. About the only thing that consistently might run 35, it would be a system that's set up on a fixed board that's got a wide swinging load. The vast majority of the systems I never want to see below 38. The reason for that is just for the simple fact that you have to start factoring into the load. I don't want to get too far into the lesson with that, but my personal, when I start seeing below 38, I start asking a lot more questions. As long as I see at least 38 on that, I'm a lot more comfortable with what that system is doing. Now 45 is a really great number as long as you're dealing with a standard system. To critique that even further, I would move that as far as 50 degrees. The reason for that is the further we get down the road, the more you're going to start seeing high efficiency systems. High efficiency systems with those with higher efficiency coils, specifically micro channel evaps, you're going to start to see that saturation temperature increase if the system's set up properly. Now you can still make those high efficiency systems run at these parameters, but you've got to make things not run at their peak performance to do that. The vast majority of the time, they could, technically, if you go by the book on those, they could be as high as 55 degrees and be normal saturation. Because part of the goal there is to get the saturation temperature closer to the return temperature, which inevitably what you end up doing is they're trying to reduce the head pressure, and that's where your compression ratio comes from. Okay, I'm about to get into a little bit of a deep nugget here, but efficiency is built off a compression ratio. That's part of why these saturation temps are very important. So when we start talking efficiency on a system, that efficiency is built off of that compression ratio. The higher that ratio, the more energy that compressor is needing to use to move the refrigerant. The lower we can make that ratio, the less work the compressor is doing. Because that ratio is factored, anybody know the formula? How is compression ratio factored? It is discharge pressure divided by suction pressure. That gives you your compression ratio. We want that ratio lower. To do that, we have to get the head pressure lower and or also increase the suction pressure to decrease the gap between them, right? So that's what high efficiency systems do. They've got huge, massive, efficient outdoor coils. Their sole purpose is to run a lower head pressure. Well, to take it a step further, we can only make the condensers, it only makes sense, and not only just from an engineering perspective, but also from a cost perspective. It only makes sense to make that condenser so big, right? And we see them get just stupid large for condensers. I mean, heck, they're as tall as Curtis sometimes. They're just crazy. He could stand up inside some of them. 5-ton condensers. But the point is, that's where they're taking it. So that coil can only go logically so big. Well, then it also made sense, okay, well, if we can only bring the condenser so far down, because there is a limit to that, we can only go down as so far. We also need to increase the suction. Well, in order to bring up the suction saturation, we need to be able to transfer more heat into that refrigerant. How do we transfer more heat? Well, we have a bigger evaporator coil and a more efficient evaporator coil. And that's when you start seeing these what they call them W and N style evaporators, where they're just folded in on top of themselves the way they are, and they're micro channel, and that is them trying to achieve more heat transfer, which we're starting to get kind of into that load talk again, where the more heat you put to a coil, the higher that saturation is going to be, because there's more heat to process. That's just how critical those saturations are, because all this everybody gets hung up on pressures, especially old school techs. I love them to death. I was there at one point myself, but pressures mean everything. Pressures in my book are only just a means to an end. That's all the pressure is. What's most important got nothing to do with the pressure, it's the saturation itself. Pressure is just there to tell you what your saturation temperatures are. Once you know what those temps are, you dive in deeper from there. Doesn't matter if it's 410A, R22, 407. The pressure is just a means to an end. And people that try to get hung up on the pressures, just from experience, tend to struggle with understanding the system, especially if they're used to seeing 410A every day, and they walk over and see a 407C system that's got a glided blend. People's minds start blowing. But if you understand saturation and get away from just relying on the pressure, it doesn't matter. It doesn't matter what you walk up to. It doesn't matter if it's got a glide or not. It is what it is. We will pause there. Glide, refrigerant glide. 407C is probably one of the most common ones we run into today. There's a different saturation scale in the condenser than there is the evaporator. You can't use the same scale for both. You will screw it up. It sounds kind of backwards. In the condenser, you use your bubble chart on the temperature, and in the evaporator, you're using your dew chart. We have to remember those things, because we will get in trouble. All of that ties back into saturation.
So do that for you.
So I'm glad you brought it up. Most of the time, if you're using digital apps or even your pressure manifolds, if they have, the analogs have the 407 on there, that's automatically built in. You don't have to put a whole lot of thought process into it. But if you do have a system that doesn't automatically generate that for you, or say the analog gauge doesn't have that temperature scale for 407, you have to do that yourself. And I highly recommend the Danfoss refrigerant slider. The Danfoss refrigerant sliders is my most recommended app for that. And it has a toggle button on there to switch between bubble or dew. And you have to make sure, depending on which side of the system you're reading, you're on the right setting. Because if you do some tests, it could be, I think some of them are up to 10 degrees difference, in normal operating range. It's really critical we pay attention to those things. Again, we start talking efficiency. All of this is built into efficiency.
When you click on refrigerant, it doesn't allow you to change that. On 407C, it does allow.
Yep.
410A, it does also allow you to change.
The blends are the ones that are going to get you for that. If you look at 404 also has it. 404A. The 400 series refrigerants, if you don't know, are your blends. So if it's got a 4 in front of all those numbers, that is a blend, period. So 407, 404, 410. Now, one thing about 410 is so they call it a near azeotropic blend. Meaning that the glide is so small that it basically has no actual impact. I think it's a zeotropic blend, are the like 407C, 404A. Those are zeotropics, I believe. It's something like that. The point is, depending on the blend, will depend on it. 410A matters very little. You can accidentally get the wrong one. You're going to see such little impact. It's not going to make that big a difference. It literally, in some cases, may be 1 or 2 degrees. That's it. Where a 407C, 10, 12 degrees in some cases. What I'm looking for, depending on the system, I want to see 38 to, I'm comfortable with 50. The only ones that go to 55 are the like 20-something SEER systems that I've seen. And it's so rare for us to run into those. Just be aware that they exist. is really the big thing there. Most of those systems, you start getting into, the regular split system condensers are going to have multiple compressors. Or there'll be an inverted compressor. By the time you start hitting that high of a SEER, which commercially is beyond rare to run into. A lot of that's being put in residentially. These are my preferred. This is what I'm looking for. Anything below this, I start asking a lot more questions. Anything above this, again, I'm going to be asking questions. It's going to completely depend on the scenario. Anything between there, I'm pretty stinking happy. Condenser, what are we looking for?
Don't let it go below 90.
Well, I mean, it rains, but.
Depending on the system, yes, 15 to actually about 30. 30 to, depending on how old and decrepit it is, 35. But it's usually because there is actually something going on there. 15 to 30 is the set standard range. Again, that comes straight back to efficiency. It's not uncommon for us to run into condensers nowadays that only run a 15 degrees split between our approach on saturation differential, right? The difference between ambient temperature outside and condenser saturation. It's not uncommon to see 15 degrees nowadays, even though the rest of the system is not that high of a SEER. The whole point for that is strictly to try to get that compression ratio down. The whole point. That's why many of your microchannel coils tend to be very sensitive. Linux catches absolute hell out of their microchannels because the way they put them in such tight tolerances when they built them, especially their earlier series. They've gotten a little bit better about it now, but you have to wash them multiple times a year for them to even have a chance of running. That's something Linux learned very hard way when they were really trying to push a lot of that forward. They came up with some very well-working systems, but they ran into problems when doing it. The point is, the microchannels are a lot more sensitive, and they've gotten a lot better at designing them and utilizing them. But you'll run into a lot of the older microchannels when they were first being put out there. You're very likely to see a lot more issues with those. You're very likely to see them. They don't have to look very dirty at all. There was a property I used to service, had 6 of them. That little package units. Every single time the lawn crew would come by and mow once a month, somebody'd have to go in and wash the coils the day after because all the units would start tripping high head. You show up and it wasn't that much on the coil. And it wasn't a real dirt patch spot. It was just a simple fact that a couple of loops around with a mower in a close proximity with the units running was enough to start tripping high heads. You'd walk up, you wouldn't think it would be the case just by looking at the coil visually. As soon as you wash it, everything would be good. They were perfectly fine until they mowed again. 15 to 30. Again, that 25, 30 is going to be most of your older systems. And when I call older, I'm talking, 10 plus years. But anything in the last 10 years, this number, the newer it is, this number is going to go down more and more.
Does humidity affect the condenser load, like the amount?
No, it does not affect the condenser, specifically the outdoor coil. In that case, because the condenser is only worried about a sensible temperature, it is not worried about a latent load.
I was just wondering because they always had like the wet bulb travel on the charging charts of the old systems.
On the old systems, because they charge via superheat on the indoor coil most of the time.
And so they need to know the outside.
What they're paying attention to is they're taking a load calculation on the indoor. And they're factoring in the indoor wet bulb as part of the load calculation for the charge to help you tune it in. Because if you look at the wet bulb it's asking for is the indoor wet bulb at the return. Because the latent heat is still a heat load and it does impact the indoor coil. It does not the outdoor, but it does the indoor. And we'll get into that more as we go. Superheat and subcool. Obviously they play a big part into this. So what is our set standard superheat value that we're looking for the most? I got 1220, 1525. I'll take a crack at it.
Somewhere in there. I mean, 20 would be depends on what I'm looking at.
Yeah, it doesn't, yeah.
Yeah. We're going to break this down into two categories. TXV, fixed bore. A TXV system, I want to see at least 8, and I'm comfortable with seeing up to 20 depending on the system. The ideal range, if I was personally doing a tune on a system where I was really dialing it in for very critical operation, say it was a cracked system, I get comfortable with this 20. Now on a fixed bore, I'm going to adjust that up, and I usually shoot for like a 10 to 25. I give myself a little more fluctuation on the superheat because I don't have actual control of it. What controls that is the load itself. And that's something you have to take into account. On a fixed board, see a TXV, if we're going to be setting it to begin with, it's usually pretty tight range, set it, and it's fine. That valve does its job. It controls that temperature. A fixed bore, it becomes really critical to look at the load on that coil, which is where that wet bulb factor comes in. And the fact of you have a high load, you've got to calculate a higher superheat. If you try to charge a 10-degree superheat at a 80-degree return, chances are by the time you get down to 72, you're not going to have a compressor for very long. You're going to start flooding back. Because as that load comes down, it doesn't have as much heat in it. It's not going to generate as much superheat. It doesn't have the ability to modulate itself. It's just going to respond via the load. Now granted, the head pressure comes down too. So there is a like-for-like relationship. As load comes down, superheat and saturation come down on the evap. So does the condenser and the subcool. They will track together, but they're only going to go so far. Eventually, if it's overcharged, which is easy to do, having too much refrigerant in there is going to start overpowering that fixed bore, and you'll start flooding back. Now, on the other hand of that, if you do have a really low load, say you've only got a 70-degree return, you're probably going to charge to that bottom end of that range. That way, once you say something ever happens, if you charge it to 25, you end up having, the system goes down, they've got 80 degrees in the space. That system's going to take a really long time to catch up because there's not enough refrigerant there. And instead of having a 25-degree superheat, which was set at 70 return, now you've got an 80-degree return. That superheat may be 40-something degrees. So we have to think about those things as we're doing that load and as we're troubleshooting those things, whether you're charging it or not, whether we're trying to evaluate, is this thing even working like it's supposed to? You got to look at the return. What the hell is the return doing? That's going to give you an indicator as to what to look for on the evaporator. Not only in superheat, but also in saturation. It's all one big piece of the pie. It works together. All four of these are completely dependent upon each other. A word of caution. There's a lot of compressors that are not going to do well for very long above 20 degrees of superheat. Because if you touch that compressor body, it will feel hot to the touch. Because you've got to make sure that this superheat's low enough to have enough cooling left in it to keep that compressor cool at 110 degrees outside. Otherwise, you start breaking the oil down. You start breaking the windings down. And eventually you end up with a failure, burnout, name it. Bearings go out because they overheat. The oil loses too much viscosity because it got too hot. It thins out too much. Now it can't cool properly. The scroll can't pump it up through itself. The Carlisle semi-hermetic pump can't move as much volume because it's too thin. Go down the list. That's all part of this calculation. That's all part of the factors we have to think about. We have to pay attention to the day's conditions that we're charging at. Because if we're charging at a mild load day, as if we're charging it at 100 degrees, by the time it gets to 100 degrees, it's too late. And now we start enabling equipment to have a premature failure that it didn't have to have. These are the things that allows the system to run 30 years but never have a problem. This is, if you set this correctly, this is how compressors can make it 30 years and never need to be changed. When they're not set correctly, they're either set too low, so you start getting occasional flood back to the compressor, and the compressor is now having to deal with that. The oils and the bearings are having to deal with that, which is really hard on them, even if you don't send it through the compressor itself. Right? It never makes it that far. Just the fact that it was allowed to touch the oil starts to mess things up. That's saying that your superheat was too low. On the flip side of that, if it's too high, now you can't cool the compressor down enough and it begins to overheat everything. And it's only going to take that for so long. We have the ability, it also depends on the design and setup and install, right? We can only affect that so far as to that point. But we have the ability to decide just how much life that system's going to have versus not. And if you have a system, say the compressor is struggling to overheat. Well, what's the superheat doing? Oh, I've got about 28, 30 degrees. All right, well, why don't we get that superheat down to about, 15, 18? Let's see if it keeps overheating. Carlisles are the most specific ones where they don't like that the most. I've had a number of Carlisles that will really buck you. The whole suction bell housing, everything will start to run hot if you put more than 20 degrees superheat to that thing. They do not like more than 20 degrees. That's where, and this is where it starts to get even further in the complication. It's already complicated just getting this far. We haven't even begun to talk about subcool. Now you start factoring multiple compressors in the same circuit. You have to think, okay, if I'm able to load more than just this one compressor, what does that mean for the rest of the system? That means I've got enough load on the system to support that. So the system is going to respond to that. So on a three compressor circuit, you're going to get completely different readings as that stages up. Now granted, you have to have enough load to support that to begin with. If you try to run all three compressors with not enough load on it, you're probably going to start flooding back. Just because it's trying to force too much cooling on the system. It's forcing the head pressure to run at too great of a pressure, and it's forcing it through into the evaporator, and it's overpowering the metering devices. So to your specific question, you have three compressors, all of them running together, they're running a 25 degree superheat. At that point, that would be justified because you start looking at the load condition. So if you got enough to have 25 degrees at three compressors, you've got enough load on the coil to support that. Now, would I love to see less superheat? Yes, but that may not be feasible depending on the setup. A perfect example of that are IntelliPacks. A lot of people get in trouble because IntelliPacks, especially dual circuit, you got two circuits, each circuit say it's got four compressors. I've seen them anywhere from 2 compressors each circuit to 6 compressors each circuit. Despite which way it goes, how many you have, say you just have one with 2 compressors per circuit. We'll start with something more simple. When you go to calibrate and adjust that system, you've got to do it a very specific way because that system stages in different ways. And you've got to make sure that those TXVs are set accordingly. Trane ends up putting one valve per side of the coil, and they split the load between 2 valves. So if you've got say a 20-ton system, you'll have 2 10-ton TXVs for the evaporator. Gonna start diving into the weeds a little bit here. Y'all just try to track with me. And part of my goal is I hope you kind of get something from this, but at the same time, this is how complex this can get. This is why we have to take our time and really think about what we're looking at. This is also a level of understanding that y'all should strive to get to. So we have compressor 1 on circuit 1 needs to be calibrated. The valve is overfeeding. So we adjust both valves, we calibrate them, right? Typically what I like to do is I like to actually adjust both valves to the maximum superheat, which is adjusting them in as far as they will go, and then start slowly backing them out together to tune those in, because those valves need to be in sequence with each other. So we start compressor 1, we check it, we calibrate everything. When I'm calibrating that compressor on this IntelliPack, I'm intentionally shooting these values high. So if I get a 20 degree superheat, I'm happy with that. Say I've got a 75 degree return on the return air coming in, right? Let's say the humidity is 50%. Let's say we got a perfect return condition. 20 degree superheat, I'm perfectly happy with. Next step I'm going to do is I'm going to bring on circuit 2 compressor 1 and test it. with both compressors together. My expectation is now that that one compressor, which is going to have a really high saturation, right? So one compressor by itself, saturation probably going to be 50s minimum. Somewhere in those mid upper 50s. I bring on the compressor 1 of circuit 2, run it together. My expectation is that superheat and saturation are going to come down. Because now you've got this large coil that's made for 4 compressors. Instead of one compressor trying to run that whole load of 75 degrees by itself, you've got 2 sharing the load, splitting the heat on that coil. So my expectation is I'm going to see that superheat come down, let's say 10 degrees, no more than 10 degrees superheat, and see that saturation come back into the 40s. That's with 1 and 1. One on each circuit. I'm going to expect similar readings on circuit 2 with just one compressor. Now those circuits are splitting the load on that coil. Everything will balance out. But that's not the only way that those can run. So that's their normal staging. The other way they can run is circuit 1, both compressors together without circuit 2. So next I'm going to stage off circuit 2 again, leave it off, and I'm going to bring compressor 2 on circuit 1 on. All right, so when I stage circuit 2 off, the pressures go back. When I bring compressor 2 on, I expect them to come back down in those same basic ranges. If at any point I see my saturation begin to drop too low, or my superheat is not maintaining a minimum of that 8-10 degrees, say I bring compressor 2 on of circuit 1. Now all of a sudden I've got a 5-degree superheat. Well, my next step is I need to now reduce that superheat, or increase, I need to increase that superheat because it worked fine with the one compressor, but when it came on with its own compressor, the 2 compressors together working the same circuit was overpowering the valve. And I need to help that valve out by pinching it off some. This was a real scenario. At an account, they kept throwing compressors. They went through 3 of them before I got there. Whenever we did the last one, this was our procedure we did, and they were very much not in calibration. And that's exactly what was happening. The moment it would stage up, it would be fine by itself. Heck, it was okay-ish with the other compressor. The moment both compressors ran on the same circuit, that superheat wasn't even there. It was just a straight flood back. Inevitably, in that particular scenario, what it ended up being is it ran by itself, just the one compressor. It ran on the high end. It was about 25-ish. It wasn't all the way to 30, but it was at 25-ish range once it was said and done by itself. But it gave enough buffer so that when compressor 2 came on, it was able to maintain about 12 degrees with both compressors of superheat. That system, in a year and a half later, has not had another failure. These are the parameters we've got to pay attention to. That is a real scenario, and I hope that gives some light as to part of your question. There's a lot of variables that play into this. While yes, it can be simple, and most of the time it should be presented from a simple mindset. But depending on how deep you need to go, in some cases, this is how far we've got to take it. At minimum, understand it far enough to go that far. Usually if I'm going to go in and do a TXV calibration, I'm preparing for a minimum 2-hour process. Minimum. I've spent an entire day trying to tune. Actually, that exact IntelliPack I was telling you about took us about 6 hours total. Just a side note, TXVs, you have to wait for them to settle. That's one thing great about things like the Testo apps, is you can chart your readings. And so every single time you make a single adjustment on that TXV, you've got to let that superheat curve flatten back out and that TXV balance. If you don't, and you're watching it constantly hunt to try to balance itself back out, and you then continue to try to still adjust it, you're going to be doing nothing but chasing your tail, and you'll never get it right. Subcool. Again, we've got 2 categories, TXV and fixed. What are our parameters that we are looking for?
812, right? Somewhere around there.
812?
Depending on the condenser, because sometimes it'll be down to like 2 or 3 degrees if it's a split system, like a high efficiency split system.
Okay. 812? 812?
14.
You mentioned on one of these VRS systems that it can be a cool.
Yes. 812 is a solid number. That's honestly the troubleshooting number to shoot for. The reality is we could do 8 to 15, depending on the situation, would be acceptable. Again, it completely depends on the equipment. But I'm going to put 8 to 15 would be the target values. We'll get into that. What about fixed bore? What kind of fixed bore subcool are you looking for?
Is it going higher?
1420,
1020?
1020? Anywhere from 2 to 6 is pretty standard. It is a metering device and it should receive a solid column of liquid. You really don't do that, and you start to do that at about 2 degrees. By the time you get to about 2 degrees on your clamps and readings, you're just now crossing that border of, okay, I should have almost completely, if not totally, liquid. This is again going to come back to the load, especially on a fixed bore. High load is going to equal a high subcool. Lower load is going to equal a lower subcool. It still has a purpose. It has a meaning. Most of the time, if it ever goes above 6, you start flooding. You start overpowering that fixed bore device, and it can't contain it or control it. So you have to be really, really careful with that. You're still charging via the superheat, right? Just like with a TXV, you're technically still charging via the subcool. But in both cases, all the readings still fully apply. Keep in mind, all of this is just very general, everyday stuff. There is a ton of equipment out there that's going to operate outside of these parameters, and it be on purpose. VRVs are an example of that. Very high efficiency systems are an example of that. Chillers on a whole nother ball game. This don't mean nothing to a chiller. Completely different variables. So chillers, you start talking superheats of 1/2 degree. And that's what we shoot for. That's what we want. We want about 1/2 degree of superheat. Anything more than that, something's wrong. Take that as part of this understanding. This is not firm set for everything. But if you can understand this will get you a really long way. All these are energy values, end of the day. If you want to really kind of do a scientific deep dive, these are energy representations. This is the amount of energy content being moved from one place to another. It's as simple but yet as complicated as that. We're taking energy, inputting it into here, and doing it through X number of temperatures. And depending on what those temperatures read, represents, so we're moving X amount of energy to here. And then they have to respectively correlate, because these can only go as high as these are taking in.